So we're trying to understand why when you heat a solid, it expands. So we started off with a model called as ball and spear. So basically what it tells is you can imagine that the molecules are like hard ball and attached to them is springs, attaching them are springs. So when you pull a spring or when you compress a spring and let it go, what happens? They go back and forth, right? The movement is so that the atom or the molecule spends equal time on the left and on the right. Right? The displacement, whatever is the displacement, is on the left. The same displacement is seen on the right. So with increase in temperature, it will be more to the left and at the same time equally more to the right. Basically, your average, the mean position will not change. This being the case, why should atom expand? I mean, the space between the atom expand. It need not make room for anything new. So the expansion idea this model does not support that expansion idea. It's able to explain what might be happening with the atoms, but it is not giving us a satisfactory answer. So the next model does a better job, and that is your real atomic model, asymmetric MOS, or Lennard-Jones potential. Basically, this is what it is. Let me show this actually. Right, instead of your simple curve like this, okay, instead of a simple symmetrical curve, we are looking at asymmetrical stuff. Right? So in this case, you guys happen to see this, na? So what is that you're able to observe? Observe this actually. Right? Now let me play the other one. You watch 1 or 2 cycles, then I'll explain. So it's still on the right, guys. It's still going to its, it's reached its maximum. It's coming back. So what's happening? Observe. Okay, let me guys give you a clue. You need to be able to answer how much time the atom or the molecule is spending on the right compared to the left with 3 as its mean position, right? With this as its mean position. How much time is it spending on the right compared to the left? It's a simple answer. It's more, less, or equal. So that's the question, and those are the options. So clearly it is going to spend a lot more time on the right than on the left. Okay, if I increase the temperature, this is the least that I'm able to simulate over here. Of course, I can still further make it as -2 and all of that. I just have to change the code a bit. So point is, it's going to spend a lot more time on the right than on the left, even for lower temperature as well. It's going to spend a lot more time on the right than on the left. So this being the scenario, you have, and it is not like this, it's within that space and it's equipotent. No. Here the mean position is somewhere over here, there. Its mean position is not exactly at 3. It will shift. As in when the temperature increases, it will shift. Actually, mean position, when I mentioned 3, I just trying to make you guys observe. But here, I don't know exact value on the right. We can calculate it and actually find it. And on the left, it is somewhere over here, 2.6 or something. So if you take the mean of it, it might be 4.5 or somewhere here, maybe 4 also. So point is, it's spending more time on the right than on the left. That's the important observation you have to make. Now, with that observation, let's read the theory part. So now it's just a matter of reading through. So a realistic model, imagine the same 2 atoms, but now the bond is not a perfect spring. Okay, so it's not a perfect spring. It does not work like that. The key feature of the real interatomic potential, on the left side, we have extremely steep scenario. Okay, and the bottom, we have a gentle minimum at equilibrium position. So somewhere along here. On the right side, rises slowly. Things rise slowly. So basically, we are looking at weak attraction. So this is because of weak attraction. And the curve turns out to be highly asymmetrical. The same energy diagram as below, the meaning holds the same. The curved line represents your potential energy. The red line represents your total energy. And the difference, the vertical line that I have not shown, I have shown over here. Right, I have shown over here this blue line that represents your kinetic energy. Here too it holds the same meaning, but actually again here I have not shown. But yeah, the meaning holds the same. And what changes because of asymmetrical? So now we're looking at what exactly happens because of asymmetry. When total energy increases, that's when we heat, amplitude becomes larger, right? So basically it needs more space to vibrate. Amplitude, it comes from your waves topic. On the left, atom hits the steep wall, quickly bouncing back. That we saw in the simulation as well, right? Now you can see that. Oh, it went off. Okay, anyways, eventually it'll come back. On the right, the wall is gentle, atom moves slowly and spends more time at larger separation. So you can see over here. Now I think it'll start coming back. Still not. So now it will start coming back. As a result, the oscillation is no longer symmetrical around R0. The average position starts shifting to the right. And the average interatomic distance becomes larger. Okay, now it's coming back. So you can see the amount of time it spends on the left, hardly few seconds. But on the right, quite, I'm not counting, but it's large. We can clearly see that. So average position shift to the right. So what is the result of this? What is the effect of temperature? At 0 Kelvin, minimum energy, almost no vibration. So this we'll understand later. As the temperature rises, vibration energy increases, average separation increases, the whole solid expands. Conclusion: why solids show thermal expansion? Thermal expansion happens because atom becomes stronger when heated. Real potential is asymmetrical. Atoms spend more time at larger separation. Average interatomic distance increases with temperature. Okay. And so the asymmetry of the real interatomic potential is the true reason solid expands on heating. Okay, guys. So this is the bit more practical explanation of understanding why objects expand when on heating. Solid expand on heating. Okay, still now it's coming back on the left. Now it's coming back. So it's a very hard push and yeah. Okay, so you guys can have a look at this.